Good afternoon, everyone. My name is Sabri Quintero. My teammates are Rommel, Medina,
Obella, Jorge, Franco.
and we're here to present our senior design project, which is NISAP 1U. So, brief project description: we're building a 1U Picosatellite that can perform duties such as monitor weather changes, track tropical systems, cloud formations, track sea level rise, changes in vegetation, and detect fire hazards. Little background behind the CubeSat program. It was started in 1999 at the California Polytechnic State University, and the goal of this program was to standardize the design of picosatellites. The FunSat competition happens every 2 years here in the state of Florida, and is sponsored by the Florida Space Grant Consortium. FIU has already participated in this competition in the past 4 years with the design of 2 3U picosatellites. Also, the Near Earth Explorer was created here at FIU on January of 2016.
Okay. For the structural constraints of a 1U picosatellite, the dimension has to be 10 centimeters by 10 centimeters by 10 centimeters. Its weight cannot exceed 1.33 kilograms. Also, its center of gravity is located 2 centimeters within the gravitational center. We choose the aluminum alloy 5052H32 material for a structure because it's a strong material, it's easy to weld, and it don't corrode easily. We came up with some designs. Our first designs are hermetic. We came up with a hermetic structure. We push in the walls. That way we have a stronger structure, but it doesn't work for us because it gives us less space inside for our components, and also it doesn't have any accessibility. For our second design that we came up with, we designed a mechanism of a sliding door. This door is attached to the top beam, and then we also push the walls outside to the outside structure. This gives us accessibility. This door gives us easy accessibility to put all the components and do all the connections inside the structure. But at the same time, this one doesn't work for us because we compromising the integrity of the structure by removing the beam from the main structure. This is our third and proposed design. We keep the same sliding door, but this time we're going to leave the top beam attached with the whole structure, but making it thicker, thinner. That way it allows us to have a gap in between to slide our door, and have an easy access for to put all our components inside and do all the connections, and also have a very strong structure.
One of the things that we have been doing throughout this semester is to start the thermal analysis on our system. We want to ensure that all the components that we're putting inside our satellite are going to be safe when operating at the extreme temperatures of outer space. So the first thing we did was to look at each component that we're planning to install and look at the working temperature range that they have. We found out that we have a temperature range that starts at negative 33 degrees and it goes all the way to 125 degrees Celsius. But the lithium polymer batteries impose a constraint on our system. The operating temperatures go from 0 to 45 degrees Celsius, so we decided to make that our target temperature. Next thing that we did was to list the sources of heat that the satellite is going to face when it's deployed in outer space, and they're labeled here in table 1. And next, we did some basic assumptions to simplify the equations that we're going to be using to complete this first analysis. So these are the basic equations that we're going to use to obtain a steady state temperature of the structure when it's deployed. The first equation shows it accounts for all the heat sources that are reaching our satellite, and the second one is the emission of energy that our satellite is going to be emitting to the environment. Once we plug in the numbers, we get a steady state temperature of the surface of our satellite of 151 degrees Celsius. And if we do take into account the solar panels that we're planning to install, that temperature goes down to 61 degrees Celsius. Table number 2 is displaying some different scenarios that on which we apply the same equations and the same values before, and we get some steady state temperature for those scenarios. Next step that we need to do with our thermal analysis is the design of a thermal insulation layer. Previous teams that have worked with the Near Earth Explorer Club already used the material aerogel. So we're going to go ahead and use that same material, and through the use of simulations, analysis, and the actual calculations in paper, we're going to decide what's the appropriate thickness of that insulation layer. The next, another field or area that we've been approaching in this semester is the calibration of our thermal sensor. This is a step that is not just going to help our team, but it's going to help the other teams working in CubeSats here at FIU, because it has never been approached by any other teams in the past. The results from this calibration are going to be shared with all the other teams. So this is a sample of the data that we're collecting to complete the calibration of our systems or sensors. We're doing collecting data at cold temperatures as well as high temperatures. It is very important for us to collect data at the temperatures that that the sensors are going to be exposed to once they're deployed in outer space.
For the altitude system, we have two control parts that are the altitude determination and the altitude control. For the altitude determination, we have two sensors, two main sensors. One of is the LSM sensor that contains a 3D accelerometer, a 3D gyroscope, and a 3D magnetometer. The 3D in this case represent the measurement in the X, Y, and Z direction. This one is going to work in conjunction to the sun sensor to determine the position, orientation with respect to the sun. For the altitude control, we're going to create a torque bar, shown here, that is going to place on the principal axis of the satellite. This one will produce a torque to change the direction of the satellite. Also, we have to have in mind that we have an air magnetic flux that to create a torque that will affect the direction of the satellite. For the design process, we divide it into steps. We have the velocity calculation and the torque calculation. In the velocity calculation, we are looking for what is the requirement force that needs to be produced by the torque bar, using a momentum equation that is the mass times the velocity. In the torque calculation, we are given some values as the wire length, voltage, core radius, and the core range to obtain the torque and the force that we produce the torque bar. For our final design parameter, we are following the requirements that need to be the force that needs to be produced by the torque bar, and this is we plug some number into the equation, and we came up with the force that needs to be produced by the torque bar that is required to produce.
For mission description, we're going to operate in an orbit of 600 kilometers, and from there we're going to be able to collect data from the atmosphere, also photograph our ocean levels and vegetation, and detect hazards to human life. And also we're going to be able to conduct cloud studies and be able to track tropical systems. Our mission requires a certain payload, which includes a thermal camera, a high definition camera, and a through the lens camera. For the through the lens camera, we are going to modify its optical system and use compound lenses. The benefits of using compound lenses is to maintain focus while zooming, and also we can decrease the total focal length and size of the system to be able to fit into a one-use satellite. We're also going to be using achromatic lenses in order to widen the range of wavelengths that we're able to collect and be able to collect more data, and also that helps. We're going to be able to help us maintain the same focus and produce sharp images. These are some of the formulas that are crucial in order to determine the overall size of the system. For our power source system, we're going to incorporate solar cells, which operate at maximum efficiency of 29.3%. We're going to gather power from solar radiation and the Earth's albedo, and in order to maximize the amount of sun energy or solar energy that we can get, we're going to maintain a sun synchronous orbit. And the total maximum area available within the satellite panels in order to install solar cells is 298.25 centimeters square. This is going to let us install 5 solar cells in each one of the panels, except for the bottom one, in which we're going to install the cameras. Also, the power source system, the solar system is going to charge our lithium polymer batteries, which is going to power all our components. For related status, we're going to follow QSAT design specification number 13, which includes many standards set up by NASA and military. And for our communications subsystem, we're going to follow the standards by the FCC. For our global design, we're going to incorporate a multi-language manual. We're going to use SI and English units. We're going to collect the data that is important globally, and it's going to be readily available for everybody around there. And also, we're going to use our modeling and engineering drawings are going to be developed to adhere to industry standards. This is a Gantt chart, which includes all our project, everything that we've done so far in the project, and where we're looking forward to move in the future. Right now, we're finishing up modeling and simulations. For future work, we're going to work on finishing our power subsystem, designing our bus subsystem, modeling, finishing modeling and simulation, and working on ground station and building and testing of the setup. Thank you very much. Any questions?
So you guys said that you were going to use 33 gauge wire for your torque bar? So what you guys said? You guys are going to use 33 gauge wire for your torque bar?
34.
34?
Gotcha.
That's going to be a bit difficult to handle. And it might not do too well in the environments you're expecting to see. I'm not the most knowledgeable person when it comes to torque bars, but in terms of wires, the smallest gauge you'll see is about 26 gauge, and that's purely because of environmental loading, and I'm assuming that you're not going to be in a very fun environment if you're launching into space. So I would see if you can change that gauge to something a little bit bigger for your sake and your sanity when you're trying to build this thing. The other thing is, in your modeling, I hope that you guys model the wire harnesses, because it seems trivial, but it's like it's a pretty significant amount of weight considering that you have 1.3 kilograms. I'd also make sure that you double check your materials, because outgassing is a serious concern since you guys have pretty much only optical sensors, and if you outgas in such a small like size, there's a pretty high probability that you'll get something on your lens, and then your entire project is a bust pretty much. So just make sure that you are very cautious with your material choices and with your wire gauges, because it'll be a guaranteed total to build if you don't do that.
Yeah, it's definitely something we'll take into consideration. Any other questions?
Yeah, you had stated that the lithium cells operating temperature, max operating temperature is around 45 degrees C. And you said that the surface can get up to 151.97 C, and with solar cells it comes down to 61 C. What are you doing to be able to ensure that you've managed the temperature in the system so that you're in the optimized range for
Okay,
power
so
source?
the reason we stated those values at the beginning is so we can just state the fact that we need an insulation layer, and so that's why I talked about the air gel. And this is that layer is the one that is gonna keep the
So how far will it take you down?
well, that's one of the things that we have to do in next semester or during the winter break. We need to do the simulations and do the actual calculations to see center amount of this material. We reduce the temperature from this number to this number. So we still need to do those calculations and run those simulations to get you an actual number, an actual value for your question.
Okay, and remember it's steady state. This is a
Correct.
satellite.
Correct. Yes.
Okay, thank you.
So when you're on the dark side,
Yes.
how are your batteries going to work if you're telling me that you're going to be at negative 150 C?
Again, in the assumptions, I didn't mention each one, but we're going to have heat that is going to be generated from inside, from the internal components. And our installation is not just going to work keeping the heat out, but it's also going to keep that heat generated by the internal components inside. And that's why we're hoping that we can maintain a safe temperature for the components when the satellite is eclipsed.
So let's say that your internal components don't generate enough wattage. What do you do?
Well, we'll have to adjust the thermal insulation layer, the thickness of the layer. Well, no, that doesn't approach your question. Well, I actually have not considered that yet.
We have heater packs. We do have heater packs.
Yeah, you just put a heater on it.
Yeah, well, exactly. Looks like the right answer, right? So yeah, we should come up with a system that can, if it's not generating heat, then we can provide that heat somehow to the systems, make sure that they stay in that safe temperature that we're doing.
Do you have instrumentation on your satellite to determine the environments that it's going to be living in? To verify that your system
yes, we have the sensors, the ones that I talked about, the calibration, EMT36, and they're going to be providing all the data about temperatures and any changes on temperatures that we might have on the operation of the satellite.
And one last question. This is a NASA satellite, so I'm assuming you guys have testing requirements to meet?
Yes, the CubeSat program states that we have, there's different kind of testing, mechanical testings, and yes, everything is laid out on the CubeSat specification manual. And so yes, there is mechanical testing that need to be successfully passed if we want the satellite to be launched. Any other questions?
I have a question about your timeline. Can you bring it back up, please? Okay, so according to your timeline, you are going to be ready with your final presentation in May, and your thesis paper in May, right? It's my understanding the final presentation is in April, and the thesis is due in April.
Yes, sir. That is actually a mistake that was recently addressed to us, but it was too late for us to
adjust it. So you're going to adjust your testing?
Correct. Everything should be adjusted accordingly to meet that April presentation and final paper to their name. Yes.
So actually, I'm gonna do another scheduled question. Your project is due in April?
Oh, whoa.
No, not here, for NASA. When do you have to
The project is summer 2017.
Okay.
So, but we don't want to leave this project for different senior design project team to come and finish it for us. So we want to be done with all the testing, with the building, everything. We want a working satellite before we graduate, or hopefully graduate on April.
Okay, so if you need to have a working project in April, that means you only have 2 months of testing, right?
Correct.
All right. Now also, you're showing here that you should be starting prototyping in 2 days, and your analysis should be completed. But from the questions these two gentlemen asked, it looks like you still have analysis, and some of the analysis you're actually doing over winter break. So you need to consider that you're now a month, you might be up to a month late in your prototyping, and you're also shortening your schedule. So now your prototyping and your testing, you you don't have 5 months, you have 2. So you need to.
Yeah, well, the idea is we understand that the project is behind schedule. Is to work as hard as possible during the winter break so we can make up the ground that hasn't been covered during this semester and finish the project, have a working prototype at the end of April.
So first advice,
Yeah.
first advice I can give you before, don't work hard and try to see if you can catch up. First thing you need to do now is lay a schedule and start planning from, it's called from front to back, right? So start planning, this is when I need to finish the project. This is the date. It's gonna take me this amount of time to test. It's gonna take me this amount of time to prototype, and then it'll give you a date, specific dates of when you need to accomplish those things. Because if you start today and say, all right, we got a month to prototype, and then we need 2 months to test, you're gonna run over. So first thing you gotta do now as a team is understand where you are, what work needs to be completed, and then lay out a new schedule and work to that schedule. Because this one is no longer valid. This schedule is out of date. So that's my biggest advice.
And in addition, you need to don't think of the end of April. You think of middle of April. This is like April 17th, April 19th.
Correct.
You'll be doing it. So that's more the middle than the end.
Right. Correct. Thanks.
I've run several qual campaigns for flight hardware, and I think I've only gotten one through a qualification QCT without breaking. If you have 3 months to do what you're trying to do, I don't think you're going to have a good time testing. I think that it's valiant effort to have this CubeSat done in 10 months or 8 months, whatever it may be, but much larger, much more successful programs take several years to develop a CubeSat, so I don't feel the need to finish it because it's not a trivial endeavor to design a satellite, test it to the ridiculous NASA standards that they try to hold over people, and then actually get it to launch. One, because that's a lot of work for people, especially since you guys don't have much aerospace experience considering that you're in school, and 2, because I can probably bet money that your launch won't be in summer of 2017. I'd probably say it's more like 2018 range.
We are looking to launch to have a realistic launching date of mid-2018.
Yeah.
To have it all that's our, as a club, that's our goal to be able to launch our one new satellite in 2018.
Yeah, so like there's no need for you guys to rush through this because you don't want to do what a lot of people do, which is they make a CubeSat and it just barely passes QTP, and then when it gets into space, one, they didn't have an actual fall unit, so they tested what they were going to fly, and then by the time it got to the flight, it was completely wrecked because it wasn't meant to take 2 flights. And then on top of that, you know, if it does survive the flight, then it gets out to space, and because it was rushed, it doesn't actually function, and that's one of the more disappointing things that you could ever do as an engineer in aerospace is design something and have to go through the most difficult part of its process and then find out that it doesn't work again, or not ever find out that it doesn't work and just assume it doesn't work. So yeah, I would say do the most that you can, document everything as well as possible, and set up a test procedure for people that follow you, and I think that's
one of our main goals of our project.
Yeah. So I wouldn't be concerned with
It's not exactly have it launch ready, but setting up like a kind of like flight model and have it so that other teams can follow and have it launch ready.
Talk to your advisors because I know you want to finish the project before you graduate, but if you as a group make the decision that this is important enough for you to work over the summer, even though you've graduated and you presented your progress up to April, like maybe you can work something out with your advisors so you can keep working this project and see it through, and not rush, as he was mentioning, rush it in the next 4 months and do a mediocre job that might not get you the satellite that you wanted to build. So I would definitely lay out your schedule, as I said, lay one out, this is what it would take to finish it by April, and then lay another one, this is what we could do if we worked all summer on this project, make a decision as a team, and then talk to your advisors to see if, what you can do about both dates.
Okay. Understand. Thank you very much. Any other questions?
Thank you.